Assalamualaikum and greetings to the lecturer. My name is Ahmad Solihin bin Muhammad Razi. My matrix number is AE220021. So we're from Group 7, Section 1, and here we are going to present our project presentation for Transform Circuit BEV 20203. So here are our group members. There's 4 person in our group.
So this is introduction. I will simply introduce about the RLC circuit. So overall, RLC circuit is a circuit that contains resistor, inductor, and capacitor. And as you can see here, it's a very fascinating and versatile electrical system. So when these components they are connected in series, they share the same current, but the voltage across them are different because of their phase relationship. So they will need additional vectorial to determine the total voltage. In this assignment, we have three main objectives. The first one is to find the current at each branch. The second one is to find the voltage at each node. And the third, the last, is to find the power dissipated in the load component. So our load component is mainly consists of a resistor and an inductor. The software we use to perform the simulation is Proto, which is a application that you can find in any app, any phone. It is available in Play Store, so everyone with phone can use it. And this app is really easy to use. You don't need high programming knowledge to use it. Just drag and connect the component, then you can read the value from it. You can display current, voltage, and power of each component.
Assalamualaikum warahmatullahi wabarakatuh. Now, I would like to present our project circuit simulations. Uh, this time, our group only use phone to simulate the circuit. We use the application that name is Proto that's suitable for Android. First of all, we need to make the circuit connections. Add all the components involved in the RLC circuit, such as the power source, resistor, inductor, and capacitor. For the next step, we do not forget to add a ammeter to the circuit. Uh, that is to record the total current of the circuit. And then we connect all the components according to the circuit picture that has been designed it before this. Uh, we need to be careful in connecting the circuit from one point to another point so that no errors can occur while the circuit is running. Uh, After that, click on the source and select the frequency. Set the frequency to the standard frequency, that is 50 Hz. Click on the current and set it to maximum. After making some settings, the circuit seems to be running well. Uh, so for the next part is uh, click on the waveform to see the circuit waveform. To see more clearly, the slow the simulation speed setting, and we set to 103 microseconds. This step is done because to see the stable output state of the circuit. Next, rename the resistor to the load. Finally, the result is M1 is 1.88 milliampere, M2 is 8.86 milliampere, and the current for M3 is 6.976 milliampere. That is all from simulation. Okay, we move to the result and discussion part. Uh, for the DC analysis, inductors behave like short circuits because in DC there is no change in current. So the inductor oppose no resistance to steady state current. Next, capacitors behave as open circuit because they block the flow of direct current once fully charged. After that, we can simplify the circuit. Uh, we replace the inductor with a short circuit, effectively removing it from the equation. We also ignore the capacitor, treating it as an open circuit. As a result, the circuit reduced to a simple parallel configuration of the resistors connected directly to the voltage source. Uh, this, simpli- this simplified circuit make it easier to calculate the voltage, current, and power distribution for DC analysis.
And now for the manual calculation part. This is our circuit, and we need to convert all the components into S domain, or we can call it J omega. Then when R convert, it is still the same and no change. For the capacitor, it will convert using the formula 1 over J omega C. And for this situation, our C is 10 micro, so we get 1 over J omega 10 micro, which also can convert into 100K over J omega. And the 1 Henry inductor, when we convert, it will turn into J omega. And now for the ft is the function for the voltage. And when t is 0 to 1, the voltage is 5. And when the t is 1 to 2, the voltage is negative 5. And to calculate the A naught, we use the formula 1 over t, integrate t and 0, ft dt. So when we insert the function into this formula, we finally will get A naught is equal to 0. Now we need to find the an and bn. An formula is 2 over t integrate t0 and with the function ft cos n omega t. For the omega, omega is equal to 2 pi over t, and our t is equal to 2, so the omega we get is equal to pi. And then we substitute into the formula, we will get an is equal to 0. And now for the bn of the similar formula with an, but only the an is cos and bn is sine. And then we substitute the value into the formula, then we will get uh, 20 over n pi when the n is odd number, and 0 when n is even number. Okay, when we found all the a not an and bn, we can substitute back to the formula, and we will get 20 over pi sine pi t 1 over 3 sine 3 pi t plus 1 over 5 sine 5 pi t. And furthermore, we can control this equation into ft equal to 20 over pi, and from k equal to 1 to infinity, 1 over n sine n pi t, and the n is equal to 2k minus 1. Next, we need to find the total impedance, and since we have the parallel part, so we need to solve the parallel part first and then the series part, and we will get this value. And now we need to find the V naught, which is the voltage at the load. Here S is equal to J omega n, and also equal to the omega naught n. Since the omega naught is equal to pi, so the s can substitute n pi j, and then we substitute and we will get this equation. When the n is equal to 1, we can substitute the n into the formula, and the V naught for N1 is 3.18 with negative 90.81 volt, and N equal to 3, V naught is equal to 1.06, negative 92.4 volt, and when N is equal to 5, V naught is equal to 0.635, negative 94.04 volt, and we will get the V naught equal to 3.18 cos pi t negative 90.81 and plus 1.06 cos pi t minus 92.4 plus 0.635 cos pi t minus 94.04 volt. After finding the voltage, we need to find the current by using the formula Vs over Z total, and this is the equation. And then we substitute the n with 1. The IT is equal to 3.184 with negative 89.2 ampere. And when the n is equal to 3, the current is 1.12 with negative 87.6 ampere. When the n is equal to 5, the ampere is 0.064 with negative 85.9 ampere. And then we conclude all the ampere, and we will get 3.18 cos pi t minus 89.2 plus 1.12 cos pi t negative 87.6 and plus 0.064 cos pi t minus 86.9, and furthermore. And finally, we need to find the power using the formula VDC times IDC plus 1 over 2 Vn In cos theta V minus theta I. And for the DC part, our DC is 0. So we only calculate the AC part. So we substitute into the formula 1 over 2 times 3.18 times 3.18 cos, and we finally will get the power equal to 5.66 watt.
In conclusion, RLC circuit exemplify the intricate and dynamic interplay of resistors, inductors, and capacitors, showcasing their unique roles in controlling electrical behavior. Whether configured in series or parallel, these circuits highlight the importance of phase relationship and vectorial analysis in understanding voltage and current distribution. So by the reference, we use these five sources, each from book, website, and also the YouTube video.